Today you're going to look at series and summation notation, and I want you to be able to evaluate the sum of a series expressed in sigma notation and also to write the rules for sequences. So let's just do a little bit of review here. Remember that n represents the term number, and you'll hear me say that very many times. It's very important for you to understand that n is the term number. Recursive sequences use the previous term, and explicit sequences, I think that's spelled wrong there, sequences, use the term number in the rule. Sequences are a list of numbers that often form a pattern, so 2, 4, 6, 8, and we worked with those yesterday. A series, the only difference between a series and a sequence is a series is the sum of the terms of a sequence. So if we're looking at this, you notice that the sequence is a list, 1, 2, 3, 4, or 2, 4, 6, 8, or fractions. But when we go to a series is the sum. So we're taking the sequence and we're, instead of putting commas in between them, we're putting addition signs in between them, and we're adding them up. Now, many series are infinite. And you'll see this would be an infinite one, this would be an infinite one. And do not have defined sums. You can't add up to infinity. In this case, a lot of times we'll just do partial. Sums are often found. A partial sum is indicated by S sub n, and n is the term number. It is the sum of a specified number of terms of a sequence. So if you look over to the side here, if we want to look at the even numbers, okay, well, even numbers start with 2, and if we want to find the sum of the first term, that's just 2. If we want to do the sum of 2 terms, it would be 2 plus 4. If we wanted 3 terms, 2 plus 4 plus 6, and so on. So that would be the sum of the first 4 terms down here. Now, a series can also be represented using summation notation. And this notation uses the Greek capital letter sigma, and it looks like this. It's used to denote the sum of a sequence defined by a rule. Now, yesterday you wrote some rules, so today you're going to, instead of just writing a rule, you're going to find the sum using a rule. Okay, now let's write each of these in series and summation notation. Okay, so we have 4, 8, 12, 16, 20. Well, just like yesterday, you need to first figure out if it's linear, linear, quadratic, or exponential. So let's try subtracting first. We have 20 minus 16, that's going to give us 4. 16 minus 12, that's going to give us 4. 12 minus 8, that's going to be 4. And 8 minus 4 is going to be 4. That means this is linear. And from yesterday, we take the first term, so 4, plus the common difference, which is 4, and multiply that by n minus 1. Okay, now that's going to give us 4 plus 4n minus 4, and then we can see that our rule is just going to be 4n. Okay, to write that in summation notation, we need to say the first value of k, and we're going to use 1. So we'll make our summation notation, and we're going to say k equals 1. That's going to be like our counter. We're going to keep counting. We're going to start at 1, and we're going to increase until we get to the last value of k. Well, how many terms do I have here? I have 1, 2, 3, 4, 5. So 5 is going to be at the top here. So this is going to keep going around in a circle, starting with the first term and going around until you get the 5th term. We're going to use the rule for n. So the first time I would go around, this would be 4 times 1. Then it would be 4 times 2, 4 times 3, 4 times 4, 4 times 5. And then I would stop and I would add all of those values together. Okay, so with that in mind, let's look up at this one right here and let's find the sum of this sequence. So when k equals 1, just make sure I have this all on the screen here. When k equals 1, 2 times 1 is 2. When k equals 2, 2 times 2 is 4. K equals 3, 2 times 3 is 6. K equals 4, 2 times 4 is 8. When k equals 5, 2 times 5 is 10. Okay, then I just add all these together. That's what this summation means. It means take the sum of all of the terms in that sequence, the first 5 terms. So we would add 2 plus 4 plus 6, that's 12, plus 8 is 20, plus 10 is 30. So the sum of this sequence is going to be 30. Okay, now I'm looking down at these fractions, and we had a problem with fractions yesterday. And I'm going to, since these are all fractions, I'm going to put this over 1. Okay, and I can see that all of my numerators, well, they're not 1 today. They're alternating. -1, +1, -1, +1, negative, positive, negative. Okay, now here is a little trick that you can do to make your signs alternate. Always use -1. If you want the first number to be positive, then you're going to go -1 to the k plus 1. That'll give you a positive first term, and then the next term will be negative. If you want your first term to be negative, which we do here, we're going to use -1 raised to the k power. So let's do that here. We're going to put our, I'll just slide it over here, summation notation. We have 1, 2, 3, 4, 5, 6 terms. So we're going to start with k equals 1 to find the first term, and we're going to go all the way up to 6 because we have 6 terms. We know that we need the sign to alternate, negative, positive, negative, positive. So it's going to be -1 to the k. And then I need to figure out a rule. Let me put this in parentheses here. Okay, so now I can say that 1 is in the numerator, and I have to figure out how to generate my denominator. Well, when k equals 1, I don't have to worry about that. Let's just forget about the signs now because this is going to alternate it for us. So my first term needs to be 1. So if I did k to the first, I would get 1. So my second term needs to be, the denominator needs to be 4. Well, if I did k to the second, I would get, let's try that. So k squared, so 2 squared would give me 4. So the term number here is 1, so 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. So that's going to work. This is the term number, and I'm using that to generate my sequence, the denominator for my series, I should say, because it's a sum here. So my rule is going to be 1 over k squared. So let's see if that gives me my first term in my series. If I do -1 to the first power, that's going to give me -1. And then 1 over 1 squared, that's just going to give me -1. So I have my rule. I know that I want to have the first 6 terms, so I'm going from 1 to 6. So keep this in mind. That's going to come in handy anytime you have signs that alternate. Sometimes you'll start with a positive, sometimes you'll start with a negative. All right, couple of things to watch out for here that I have notes on. A series can have a first value other than k, and that's what's happening right here. Expand just means to write out all of the terms. So that's what we're going to do here. When I typed this up, I couldn't do a squared here, so that's why I have this is raised to the k power. Okay, so if I'm looking at this, you might think that you're only going to write the first 3 terms, but you need to write the second term, the third term, the fourth term, the fifth term. So there's actually 4 of them, even though it may look like it's 2. So if you're going to do that, do 5 minus 2 and then add 1 to it, and that will tell me how many, or tell you how many terms you need. So let's get started here. K equals 2. So when k equals 2, I have 1 over 3 squared, and that's going to give me 1/9. When k equals 3, I have 1 over 3 squared, and that's going to give me, 3 cubed, That's going to give me 1 over 27. When I have k equals 4, that's going to be 1 over 3 to the 4th, or 1 over 81. And when I have k to the 5th, I have to keep going until I get to the number 5, and I include that. That's going to be 1 over 3 to the 5th, or 1 over 243. Okay, so when I expand, this means find the sum of the series, and series means to add all the terms together. So I'm going to do 1 over 9 plus 1 over 27 plus 1 over 81 plus 1 over 243. Okay, now if I get a common denominator for all of these, I'm going to be able to add them together. So this would be 40 over 23. This would be 27 over 43. This would be 9 over 43. So let's just make this let's do this. That's going to be 27. That's going to be 9. That's going to be 3. And that stays 1. And these are all going to be over 243. So I'm going to add my numerators. That's kind of hard to see. 27 and 3 will give me 30, and 10 more will be 40. So when I say evaluate, I'm finding the value of this series. So it's going to be 40 over 243. Now, finding the sum of series with many terms can be tedious, but there are some shortcuts for basic, constant, linear, and quadratic series, and that's what these are right here. Now, this only works if you just have a number. So this would be the constant series right here. And what we would do with that is we would just use this, which means that we're going to take n. We need to figure out what n is. Now, just be careful here. This is 4 to 10. So that means it's 4, 5, 6, 7, 8, 9, 10. So there's 1, 2, 3, 4, 5, 6, 7. So you might be tempted to say that that's 6, but just take 10 minus 4, which is 6, and then add 1 to it. So in order to find that sum without actually going around the loop all those times, we can just take n. So 1, 2, 3, 4, 5, 6, 7, n equals 7, and we do 7 times 6, and our answer is 42. If you just have a linear series, so just a k here, you can't have adding or subtracting or multiplying anything else. It just has to be this. So these are just 3 special cases where you have shortcuts for. If that's the case, we have to take n, and n here is going to be 8. So 8 minus 1 is 7 plus 1 again. So that n is 8. We're going to use this. So it's going to be 8 times 8 plus 1 divided by 2. So that's going to be 9 times 8, which is 72, divided by 2, which is 36. Okay, now, the last case is if you just have a k squared. Again, can't have anything added, subtracted, multiplied, or anything like that. So we're going to use this, which means we're going from, from 1 to 12. So that means we're going to have 12 as n. So n equals 12. Here n equaled 8. Okay, so now we're going to follow this one. And it's going to be 12 times 12 plus 1, which is 13, times 2 times 12, which is 24, plus 1, which is 25. And we're always going to divide it by 6. Now, if you want the proof of this, there's some examples at the beginning of your textbook for some of these here, and we're dividing by 6. So we multiply all of these out, divide by 6, and you're going to end up with 250 for the sum. Okay, these shortcuts can only be used if the rule is a number or a variable to the first or second power with no other operations. Okay, here's some helpful hints. When you're deciding between linear, quadratic, exponential, subtract or divide from opposite of what you read. You're going to go this way, right to left. Linear has a constant first difference, so this is what you're going to use. Quadratic has a second difference, constant or common difference. And you're going to use n squared, and you just need to adjust as needed. So let's see, we have this here. If we just do n squared, we're going to get the first term we square it, we get the second term we square, third term we square, fourth term we square. But let's say our term that we want is going to be 3, 6, 11, 18, and 27. Well, we know that when we square it, we can get these values. So now we just need to check and see, well, how can we get from here to here? What are we doing to each value? Well, it looks like we're adding 2 here, adding 2 here, adding 2 here, adding 2 here. So our rule could be a sub n equals n squared plus 2. So you just basically use addition, subtraction, multiplication, or division to find a way to get the n squared term to match the term that you need. Now make sure it works for the rest of your terms and not just n sub 1 or n equals 1. So test your rest of your terms. For exponential constant ratios, you're going to divide a term by the previous term to get a ratio, which is your r. And then, I think you need to change yours on your paper. I don't think yours matches this. This should be the general form. It's a sub n equals a sub 1 times r to the n minus 1. Okay, so let's say for term 1, it's a sub n is going to give us, or not sub n. Okay, and we're going to just skip this example here, but make sure that you change your general term, your general form to this for exponential. And same thing as with the quadratic. By using addition, subtraction, multiplication, division, you need to find a way to get your term to match the term that you need. So we want to, let's change this to a sub n term to match the term needed, and make sure it works for the rest of the terms and not just term n equals 1. So remember, a to the n minus 1 often helps when you have found a and you need it to be 1. And remember that negative 1 to the n and negative 1 to the n minus 1 will alternate signs between negative and positive. So look for patterns. Okay, you have a few questions to try.